Start. Start.
Okay, this video belongs to the blind Nigerian scientist, Ochili Alex. And the topic we are treating today is electrolysis. And our objective is that at the end of today's lesson, a student should be able to calculate the mass of element that is discharged during an electrolytic process, during electrolysis. We'll start with the definition we gave in our earlier lesson, that electrolysis is the chemical decomposition of a compound, and that compound can be in liquid or molten form by the passage of direct current. The chemical decomposition of a substance in liquid or molten form by the passage of direct current. By this definition, we see that electrolysis has chemical effect, because electrolysis is a chemical process, we have said that, and it is brought about by the passage of direct current. That tells you that electric current has chemical effect. Other effects of electricity or electric current are heating effect. We use this heating effect, we use it in our electric lamp. When we switch on the electric lamp, it begins to glow, because the tungsten filament of the lamp has been heated up by the electric current. That tells you that electric current can heat up something, and therefore it has heating effect. Then the third effect of electric current is magnetic effect. It's magnetic effect. And this is because we can use electricity to make our magnet by electrical method. So we make a magnet by electrical method, and that tells us that electric current also has a magnetic effect. Now, today we are going to concentrate on how to calculate. First of all, we have to realize that when a compound which is in liquid or molten form is electrolyzed, that is chemically decomposed. When a compound in liquid or molten form is decomposed, part of it, one half of it is liberated at the cathode. One half of it is, an element is liberated at both the cathode and the anode. And the masses of this element that are liberated can be calculated. They depend on many factors. And some of the factors on which the mass of the element that will be discharged or deposited or liberated at the electrodes. One of the factors that the mass depends on is on the quantity of electricity that is passed through the electrolyte. Quantity of electricity that is passed through the electrolyte. The other factor on which it depends on is the valency of the element itself. We are going to see this relationship as we move on. So now we are going to move to, first of all, calculations that involve the quantity of electricity that is passed through the electrolyte. And the place we are going to start is by defining what we call 1 Faraday. We are used to Coulomb as the unit of electricity. But in this area, we're going to introduce another unit of electricity that is known as Faraday. And this Faraday, we are going to define it we are going to understand what it means by defining what we mean by 1 Faraday. So the first thing we are going to know is what we call 1 Faraday. Now, we are going now to define this new unit of electricity, which we call 1 Faraday. We are going to define 1 Faraday. 1 Faraday is simply the quantity of electricity that is required for the transfer of 1 mole of electrons during electrolysis. It is the quantity of electricity that is required for the transfer, or that is for something to gain or lose 1 mole of electrons during electrolysis. So it is the quantity of electricity that is required if 1 mole of electron is to be gained or lost during electrolysis. Now that we have known what 1 Faraday is, we are going to, based on this definition, explain how it happens. So let's take something like silver, 1 mole of silver ion. Suppose we want to discharge 1 mole of silver ion at the cathode of any electrolytic cell. Because when that silver is discharged, it will be deposited on the cathode because it's a positively charged ion which will move towards the cathode during electrolysis. Now, the equation for the discharge is Ag plus E minus, giving us Ag solid, meaning that 1 mole of silver ions will gain 1 mole of electrons to give us 1 mole of silver atoms. I repeat, 1 mole of silver ions will gain 1 mole of electrons to produce 1 mole of silver atoms. These silver atoms, of course, will be deposited at the cathode. So you see that what we have here will require 1 Faraday, because we say that 1 Faraday is the quantity of electricity that is responsible for gain or loss of 1 mole of electrons during electrolysis. Now let's take copper 2 ion for example, and the equation for its discharge is Cu2 plus 2E minus, giving us Cu solid, that's copper atoms. So you see that 1 mole of copper 2 ion will gain 2 moles of electrons in order to give us 1 mole of copper atoms, meaning that 2 Faradays of electricity, because 2 moles of electrons being gained means that 2 Faradays of electricity will be required. Remember that each Faraday stands for 96,500 coulombs. Now, if you take aluminium ion Al3+, for you to discharge 1 mole of aluminium ions, then that 1 mole of aluminium ions will gain 3 moles of electrons to form 1 mole of aluminium atoms. I repeat, 1 mole of aluminium ions will gain 3 moles of, because it is trivalent, aluminium is trivalent, so 1 mole of aluminium ion we gain 3 moles of electrons in order to form 1 mole of aluminium atoms, which will be deposited at the cathode. Now, this tells us that 3 Faradays will be required for 1 mole of aluminium to be discharged. Okay, so what is it? 1 minute.
Hey, if you look at me.
Similarly, it's not different when gases are involved. What we did before does not differ from what we have when gases are the products. So let's take, for example, hydrogen gas being discharged during electrolysis. Hydrogen ions being discharged as hydrogen gas during electrolysis. Now, the equation is 2H plus, because hydrogen gas is the hydrogen is a diatomic molecule. Hydrogen gas is diatomic. So 2H plus 2E minus gives us H2 gas. I repeat, 2H plus aqueous plus 2 moles of electrons give us H2 gas, meaning that 2 moles of hydrogen ions will require 2 moles of electrons to produce 1 mole of hydrogen gas. So, in order to produce 1 mole of hydrogen gas during electrolysis, we will require 2 Faradays. Now, we move to chlorine gas. Again, chlorine is a diatomic molecule. Chlorine gas is a diatomic molecule. So, we have 2Cl minus aqueous plus 2E minus will give us Cl2 gas. Meaning that. So when it comes to chlorine gas, we have 2 moles of chlorine gas. 2 moles of chloride ion. We lose 2 moles of electrons to give us 1 mole of chlorine gas, because chlorine is also diatomic molecule. So 2 moles of chloride ions, we lose 2 moles of electrons to give us 1 mole of chlorine gas, meaning that 2 Faradays will be required for the discharge of 1 mole of chlorine gas during electrolysis. I repeat, 2 Faradays, because of the 2 moles of electrons in the equation, 2 Faradays will be required to discharge 1 mole of chlorine gas during electrolysis. Finally, how do we discharge oxygen gas? Well, oxygen gas is divalent. Oxygen ion is divalent. Now let's see how the equation, starting from hydroxide ion. So we have 4 moles of hydroxide ion will lose 4 moles of electrons to give you 2 moles of water, 1 mole of oxygen. So how many Faradays are involved? So 4 Faradays are involved. 4 Faradays are involved whenever 1 mole of oxygen gas will be given out during electrolysis. So we can still write this equation as 2O2 minus loses 4 moles of electrons. 2O2 minus loses 4 moles of electrons to give us 1 mole of O2 gas. Okay, so this equation, that's the discharge of oxygen gas, can also be written as 2O2 minus, because oxygen is a divalent the oxide ion is a divalent ion, and oxygen gas is a diatomic molecule. So what we have here is a 2O2 minus plus 4E minus gives us O2 gas. That is 2 moles of oxide ions. We lose 4 moles of electrons. We lose 4 moles of electrons to give us 1 mole of oxygen gas. And since 4 moles of electrons are involved, we know that 4 Faradays will be required for this. So now that we have known how to know the number of Faradays, that the number of Faradays that will be required during electrolysis simply depends on the moles of electrons that will be needed for the discharge of 1 mole of the ion. So we now use to discharge 1 mole of the element. We will now, based on this, whenever we are looking for the quantity of electricity, we must know that the number of Faradays required depends on the number of moles of electrons. Okay, so having seen that, how we can know the number of Faradays that is required to discharge 1 mole. That's what we demonstrated. How we can know the number of Faradays required during an electrolytic process. We are now going to go into calculation proper. How we can calculate the mass of an element that will be deposited at the cathode or liberated at the anode. Now the first example we are going to have here, because we are going to illustrate or demonstrate this with many examples. So the example 1 here goes like this. Read the question.
Calculate the quantity of electricity that will deposit 2 grams of copper at the cathode of an electrolytic cell. 1F is equal to 96,500 coulomb.
Repeat the question again.
Calculate the quantity of electricity that will deposit 2 grams of copper at the cathode of an electrolytic cell. 1F is equal to 96,500 coulomb.
So we are told to find the quantity of electricity that will pass through an electrolyte for 2 grams of copper to be deposited at the cathode. And given that 1 Faraday is equal to 96,500 coulombs. Now, we may then see you equal to 63.5. What do you think? Having seen how we can know the number of Faradays required in an electrolytic process, we are now going to go into how to calculate the mass of the element that is discharged during electrolysis. And we are going to illustrate or demonstrate this by using many examples. And the first example here is example 1. So you can read the question.
Calculate the quantity of electricity that will deposit 2 grams of copper at the cathode of electrolytic cell. 1 Faraday is equal to 96,500 coulomb, and copper is equal to 63.5.
So the molar mass of copper is 63.5 grams per mole, while 1 Faraday is equal to 96,500 coulombs. Okay, so
that one.
Okay, so now we'll go to the solution. First of all, we'll start by with how we discharge copper ion during electrolysis. So we write Cu2 plus aqueous plus 2E minus gives me Cu solid, meaning 1 mole of copper 2 ions we require or we gain 2 moles of electrons to discharge and deposit as 1 mole of copper atoms. I repeat, 1 mole of copper 2 ions aqueous will require 2 moles of electrons to discharge and deposit as 1 mole of copper atoms at the cathode. So which means 2 Faradays are required. So 2 Faradays are required for the discharge of. So we now write 1 mole of copper. 1 mole of copper is deposited by 2 Faradays. 1 mole of copper is deposited by 2 Faradays. And we have been given the molar mass of copper as 63.5 gram per mole. So we write 63.5 grams of copper. 63.5 grams of copper is deposited by 2 Faradays because 2 times 96,500 coulombs. 2 times 96,500 coulombs. Meaning that 63.5 grams of copper coulombs. By 2,500 coulombs. Eh? Yeah, the first time. So this has to be repeated. Clean that second line. Let's repeat it.
63 weight of copper.
Yeah. This means that 63.5 grams of copper will be deposited by 2 times 96,500 coulombs. 2 times 96,500 coulombs. In the next line, we write 63.5 grams of copper. 63.5 grams of copper is deposited by 193,000 coulombs. Is deposited by 193,000 coulombs because 2 times 96,500 coulombs is the same thing as 193,000 coulombs. Is deposited by 193,000 coulombs. Therefore, 2 grams of copper. Therefore, 2 grams of copper in the next line. Therefore, 2 grams of copper. I always use therefore this symbol. Therefore, 2 grams of copper will be deposited by. Therefore, 2 grams of copper will be deposited by 2 grams over 63.5 grams times 193,000 coulombs over 1 times 193,000 coulombs over 1 over 63.5 grams times 193,000 coulombs over 1. 193,000 coulombs over 1. So, pause it.
Which is equal to?
No,
Which is equal to 6,000. Which is equal to 6,078.7.
Repeat it.
Which is equal to 6,078.7 column.
Okay, that's very good. Now, let's move to example 2. Let's now move.